Okay, good morning everyone. So we are recording now and we want to continue our discussion from yesterday to design a primal dual algorithm for minimum cost perfect matching in bipartite graphs. So let's just recall the interpretation of the complementary slackness condition, right? So if you are given, you have a perfect matching and you have a dual feasible solution such that for every edge, if the edge is in the matching, then this constraint should hold tightly, right? In this case, we know that M is a minimum cost perfect matching and the dual solution is an optimal dual feasible solution. Right, can you check with him? Okay, so let's just, all right, so here is what we wrote. Oh, and my phone is not on silent, sorry. Okay, so if M is a perfect matching and Y bar is a dual feasible solution, and let's suppose that for each edge, for each edge UW, if the edge is in the matching, then we know that the constraint holds tightly. So Y bar U plus Y bar W is exactly the cost of the edge UW. Right? So if this is true, then M is indeed a min cost perfect matching. And Y bar is an optimal dual feasible solution. And this is going to be the driving force behind our algorithm, right? We want to get to a point where this condition holds for every single edge. Right? Right. Okay, so as usual, let's start with an example, and then eventually we will formalize it today or tomorrow. We'll see how it goes. Okay, so here is the example I want to consider. U0, U1, U2, W0, W1, W2. And the edges are, I'm going to put all the edges except one edge while keeping the graph bipartite. So these are all the edges we have. We have 3 plus 2 plus 3, 8 edges. And let us say the costs on the edges are given to us, right? And remember, the costs need not be non-negative in this case. So I'm actually going to deliberately choose some negative numbers so that there is no misunderstanding. So these are 4 minus 2 minus 2. Let's say this is minus 2 and this is 2 and this is 1 minus 2 and 0. Is it clear which number indicates for which edge? Let me just make it a bit. Minus 2 and 2, and this is a 1 here. Okay. Okay, great. So this is our graph GUW, and we have the costs given from the edges to real numbers. All right. So we want to get a primal dual algorithm. We have already seen one at this point for shortest path. So we're going to do something very similar, right? In spirit, it's going to be similar. Of course, the technical details are going to be different. At each step of the algorithm, what do we want? We want a dual feasible solution, right? Every step we want a dual feasible solution. All right. And we want to keep improving the dual feasible solution until we can find a perfect matching that satisfies these conditions with the dual feasible solution. So the first question is, can someone give me a dual feasible solution? Right. Okay. So let's look at the dual constraint. What is the dual constraint? We want yu by 2. Right. Yeah. Yeah. That's so this is our dual constraint, right? It's the only constraint we have. The y variables are free. So this is the only constraint we need to satisfy. So clearly, you take the minimum cost over all edges and divide it by half and give that value to every vertex. Right? So what will happen in this case? The minimum is uh, maybe I have forgotten the assignment details. Yeah, you will find links. I have forgotten the exact questions I put in. Great. Yeah, so I deliberately did it that way, sort of, because I wanted to cover shortest path in the lectures and I wanted to start matchings after the assignment was submitted. So that is the reason I did not start it earlier. So yeah, I'm glad that you are able to see connections. It is by design. Okay, so we'll take the minimum cost, which is -2 in this case, and divide it by 2. So we'll give -1 to every single edge. Right? So let me use red color for the dual feasible solution. -1 for every vertex. Okay, so these are the labels of the vertices as we discussed in module 1. Okay. And we want to find a perfect matching among those edges that satisfy the dual constraint tightly. Right, so we are going to do something very similar to the previous shortest path one. We'll define what are called tight edges. Right? It is exactly what you think it should be. So given a dual feasible solution, y bar, we define the slack of an edge uw as the cost of the edge uw minus y bar u minus y bar w. Okay. Notice that this will always be greater than equal to 0. Right. And we will say that an edge uw. Did I start recording? Did I? I think I did, right?
Yes, you did.
Okay, good. Okay, great. Thanks. Okay. An edge uw is tight if the slack of the edge is 0. Otherwise, uw is not tight. And we want to get to a situation such that if you look at just the tight edges of the graph, there is a perfect matching in the tight edges, right? That is exactly the condition we have. We want the perfect matching, all the edges to be tight. So the goal is to reach a situation, well, what I mean is a y bar, such that there exists a perfect matching among the tight edges. Since we are considering bipartite graphs, we already know how to find a perfect matching. So we can already assume in this algorithm that the graph is a perfect matching. You can run that algorithm first. And if it doesn't have a perfect matching, then it doesn't have a minimum cost perfect matching. Right? So this is a safe assumption that the graph G has a perfect matching, or what I think was called on your assignment as G is matchable. So sometimes I may say that. Okay. All right. So let's look at the current tight graph. Let's look at the current graph with just the tight edges. Okay. We'll call this the graph H. Okay. So the tight graph at this point so let's put down the vertices. Can someone tell me which ones are the tight edges? All of them with cos -2. Exactly. Right. So you got U0 W1, U0 W2, U1 W1, and U2 W1. Okay. So this is our tight graph. Does this graph have a perfect matching? No. Okay. So it doesn't have a perfect matching. So we haven't reached our goal, right? We want a situation where the tight graph has a perfect matching. So observe that H has no perfect matching. Okay. All right. Okay. So now, is there a systematic way to find a better dual feasible solution, right? And let's see. So let me just write down the question and then let's discuss it. Right? So, how should we go about this? Let's go back to what we did in shortest paths because certain elements are actually common. So, does anyone remember how we found a better dual feasible solution in the shortest path primal dual algorithm? Right. We considered the slack of certain edges. How did we get those edges? What specific edges did we look at? Anyone in the call can also answer. Right. We looked at a certain cut. Right. There we wanted a graph where the two vertices S and T belong to a common component. Eventually we got a directed graph and all that. Those are details. But we wanted S and T to be in the same component in the tight graph or the tight digraph, whatever. Right. And until we did not reach that situation, we used a certain cut, right? What was the cut we used? All the reachable vertices from S, right? So basically, if there is no ST path, then there has to be an ST cut, right? Such that your tight edges right now do not have any edges in that particular ST cut, right? So you looked at all the reachable vertices from S, that became one component of your tight graph. And then you looked at the cut corresponding to that vertex set. Right? So there is a combinatorial thing going on beneath this whole thing, right? So we are looking at this combinatorial property. If there is no ST path, means that there is an ST cut, such that in that cut you have not chosen any edges, which is why you don't have a path from S to T. Right? Okay. In this situation, we are not looking at paths. We are looking at perfect matchings. Right? So here our tight graph does not have a perfect matching. So what should we be looking at? Sorry, deficient set. We are going to look at deficient sets, right? We have a bipartite graph. If it doesn't have a perfect matching, it must have a deficient set. That combinatorial object called the deficient set is also going to guide us in finding a better dual feasible solution. Okay. I just want to make it clear that things are not arbitrary. There is a underlying theme which you see in many of these algorithms. Right? In particular, you see ideas from optimization coming, like complementary slackness and all, but you also see ideas from combinatorics coming in, which is why it's called combinatorial optimization. Right? Okay. So the fact that this graph doesn't have a perfect matching, it implies that there exists a deficient set. Right? So I'm going to choose one deficient set. We can run the perfect matching algorithm and it will give us some deficient set. Right? So we'll choose one deficient set and try to use that to systematically find a better dual feasible solution. Okay, I'm going to choose a specific deficient set because I want to point out certain things about the algorithm. So here is a deficient set I want to choose, U1, U2. Does everybody agree U1, U2 is a deficient set in the graph H? Right. Okay. So let's choose a deficient set. Right, it could be. U0, U1 is not a deficient set. U0, U1 is not. U0, U1, U2 is, right? I'm going to deliberately choose U1, U2 since I want to exhibit certain features of this algorithm. Okay, but it doesn't matter which deficient set you choose. You run the previous algorithm, it will give you a deficient set, and that is it. Okay, take any deficient set. All right. So this is going to be our deficient set S, whose neighborhood in this graph is this, right? So this is our neighborhood of S in the graph H. Notice that we have two graphs, so we should distinguish by putting subscripts. All right. So we want to use this deficient set and its neighborhood in some sense to systematically get a better dual feasible solution. So we are going to look at specific edges and their slacks and then do some modification to the dual feasible solution, and we will ensure that we get a better dual feasible solution by doing this process. Okay. So let us consider a certain edge set. What is the edges that I should look at? Anyone in the call? What are the edges we should look at? Any ideas? You could be wrong, it's fine. From S to NHS. Right, that's good. We will do that exactly. So we will increase for some, so the vertices in S, we will increase by some epsilon, or I think I call it beta. We'll increase it by some beta. And for all the vertices in NHS, we'll decrease by a certain beta, right? And why? So before we get to the details of beta, why will this give us a better dual feasible solution? Exactly. NHS is smaller than S. So we will be increasing, in this case, we'll be adding 2 beta and we'll be subtracting 1 beta, right? So we will still increment by a total of beta. Great. So that's exactly what we'll do. We will add a certain beta here and we will subtract a certain beta here. Okay. Now we need to figure out what is the best beta we can choose, so that we can do this step. Outgoing from S into, right, the non-tight edges. Right. So let's look at the edges going from S to the neighbors of S, but not those which are already in H. Okay. So I'm going to, maybe I'll put a notation. So I'm going to look at the edges which have one end in S and the other end is a neighbor of S, but it is not a neighbor of S in the graph H. Okay. So I'll just state what this notation is. If S and T are disjoint subsets of my vertex set, then partial S comma T is the set of edges with one end in S and other end in T, right? Generally, when we write partial S, we are looking at partial S comma S complement, right? So it's a generalization of that notation. Okay. All right. So let's look at what these edges are. Okay. Can anyone tell me what are the edges in this set? So what are the edges in this set at the vertex U1? U1, W2. And what about the vertex U2? U2, W0 and U2, W2. U2, W0 and U2, W2. Okay. These are the three edges we are looking at. We are looking at all edges of the original graph G, right? So this is all happening in the graph G. If you really want, I can say here G. Okay. And we are looking at the edges which have one end in S and the other end is a neighbor of S, but it is not a neighbor of S in the graph H, right? Because the ones which are in the H, they are already tight edges. So those will give us slack 0, right? We want to choose a non-zero slack to make real changes to the solution, right? So now I want to list down the slacks of these three edges. Okay. So what is the U1 W2 slack? U1 W2 4. Yes. Okay. U2 W0 3. Okay. I am trusting you. U2 W2 2. Okay. Those are the slacks of the three edges. So as before, let us choose the minimum slack here. And this is going to be our beta. Okay. So we are going to add beta to all the dual variables corresponding to vertices in S and subtract it from all the dual variables corresponding to the neighborhood in the graph H. Okay. So let me actually cut, no, sorry. Let me just cut out the ones which I'm changing. So I'm going to change this -1 and this -1 and this -1. Okay. And let me put the new dual solutions, dual variable values for these three. So I'm going to add 2 to these -1s. So that gives me a +1 and a +1. And this -1, I'm going to subtract a 2. So I get a -3. Okay. Let's try to quickly verify. So what's not entirely clear, or what may not be entirely clear at this point, is why is this a valid operation, right? What we need to check is that doing this gives us a dual feasible solution. The fact that it is better is already discussed, right? Because we're adding 2 times beta and we are subtracting 1 times beta. More generally, yeah, you can generalize that, right? Okay. So the question is, okay, maybe not. So why does this give us, right. So the point is we add beta to each dual variable corresponding to S, vertices in S, and subtract beta from each dual variable corresponding to the neighborhood of S in the graph H. Okay, so we want to answer why this is a valid operation. Why does this give us another dual feasible solution? So notice that the y variables are free, right? So we don't care whether anyone becomes positive, negative. We don't care about these things. The only thing we need to check is that this condition is satisfied. Right? Okay, so what are the different kinds of edges we have, and what are the only edges we really need to care about? Right, right. So edges that have one end in the neighborhood of S, we don't need to care about them at all. Because if the other end is not in the neighborhood of S or is not in S, then we are only decreasing the left hand side because we have subtracted something from the vertex in the right hand colored class, right? And if the other end is in S, then we are simply adding beta and subtracting beta, right? So we won't change the left hand side in the dual constraint, right? So if one end is in the neighborhood of S in H, we don't need to care about those edges. If none of the ends is in um, right, in fact, I think we can reach the conclusion that we only need to care about those edges which have one end in the set S. Because if you are not increasing something, then you are not going to violate the dual constraint, right? The only way you can violate a dual constraint is if you are increasing something on the left hand side, right? So we can assume that the only edges we really care about are edges that have one end in S, right? So if one end is in S, the other end could be in the neighborhood of S in the graph H, in which case you are adding beta and subtracting beta, so no change. So then the only edges you have to look at are the edges going from S to vertices that are neighbors of S, but not in the graph H. Well, but that is exactly the set we were looking at. And we chose the slack in a certain way, right? We chose the beta in a certain way. So it will ensure that the constraint is not violated. I'll not do the arithmetic here. I'll leave it to you, right? But you get what you have to check. All right. So let's write down the, yeah, maybe let's check one of the edges which has one end in S and the other end in this other set. Right? Let's check one of these edges. So if you look at U1 W2, right? So let's look at U1 W2. So its slack is 2 plus 1 minus 1 is exactly 2. Remember previously its slack was 4 and now it has reduced to 2 because on one side you have reduced the beta, on the other side you have not reduced beta. Okay. All right. So I'll just say, right. So maybe I'll just say do it yourself because you already discussed it. I'm not going to write down the whole argument. Okay. And the other point is, why is it a better optimal solution? That we have already discussed, right? So in fact, I'll change the question and I'll say it's a better dual feasible solution because we are adding beta to more number of vertices than we are subtracting beta from. So the total, remember what was the dual objective function? It was a sum of all the dual variables, right? So the sum is going to naturally increase, right? Okay. Let us also make sure that we know what our dual solutions values were. I just want to write them down for the sake of completeness. Okay, so let's just write down. Previously, we started with all minus ones. So it was minus 6. That was our first dual feasible solution. Now we have, how much is it? Minus 4. Exactly. Right? We have added 4 and we have subtracted 2. So in total, we have added 2. All right. So now let's proceed. Maybe I'll want to copy this drawing and go to another page. Okay, I don't know what's going on. I'll give it one last shot. All right. Anyway, let me just go to another page and draw this whole thing. It won't take that long. All right. Okay. So we have got U0, U1, U2, and W0, W1, W2. Okay. And we have got all edges except one of the edges. We don't have U1, W0, I guess. And we have the other edges. Okay. And let's put down the costs. 4 minus 2 minus 2. And we have got minus 2 and 2. And we have got 1 minus 2, 0. 1 minus 2, 0. Okay. And let's look at our dual feasible solution that we have right now. We have got minus 1, 1, 1, and minus 1, minus 3, minus 1. Okay. All right. So let's draw the tight graph. What are the tight edges? Can someone tell me? All the previous ones. Is that true? So there are certain edges which we know for sure they are tight. Let's just take a look. Right. So the previous, right. So these edges, which have one end in S and the other end in the neighborhood of S in H, we have just increased beta and subtracted beta. So they are going to be tight, right? Okay. So let me draw those two, right? So it's U1, U2, both connecting to W1. Right. So in fact, the tight graph, one of the differences between this algorithm and the previous is that the tight graph doesn't necessarily keep increasing in number of edges. So an edge which was previously tight could actually stop being tight now. And I think we have at least one example in this case here. U0 W1 used to be tight, and now is it tight? It is not tight, right? U0 W1 is not tight. What about U0 W2? U0 W2 is tight because both ends are not in S and the neighborhood of S and H, right? So U0 W2 is still tight, right? We previously had 4 tight edges. We have drawn 3 of them here. One of the edges that used to be tight is no longer tight. Okay, I'll just put an observation. Observe that U0 W1 used to be tight, but is no longer tight. Okay, if it had been the case, then actually runtime of the algorithm would be easier to analyze. We will probably talk about runtime tomorrow. Let's see. All right. Okay, and what about the other edges? Some edge must have become tight, right? The one with the minimum slack should have become tight. U2 W2. Let's check. U2 W2. It's 0 plus 1 minus 1, right? So it's tight. So U2 W2 has become tight. Okay. So this is our tight graph H for the next iteration of the algorithm. Right? Once again, the tight graph does not have a perfect matching. Okay. Okay. Before we proceed, are there any questions or concerns? Okay. Notice that the number of tight edges is actually the same in both of the steps. Previously also we had 4 tight edges. Now also we have 4 tight edges. Okay. All right. But there is something that has improved, which is a dual feasible solution. That has improved for sure. That we know. Okay. So we still made progress. But yeah, it's because of this issue, the runtime analysis becomes a bit trickier. And to make it truly polytime, we may have to do some tweaks here and there. Okay. All right. So now, again, the tight graph does not have a perfect matching. And we want to again systematically, as we did before, improve the dual feasible solution. So there is going to be a deficient set. What is a deficient set here? Sorry. U0, U1, U2 is a deficient set. Is it the only one? Could be, right? Yeah, I think any 2 vertices have 2 neighbors. So the only possibility then is to consider all the 3 vertices. Yes, yes, yes. W0 can be a deficient set. That's right. Yes. Yeah, so you can actually choose on W0 side. I'm sticking to picking the deficient set always in the black vertices, the U set, right? But you can change it. It doesn't matter. So, uh, so let's say S is our U0, U1, U2. This is our deficient set in H. And we want to again increase the dual solution. We want to improve the dual solution, right? So let us consider the edges going from S to the neighbors of S, which are not neighbors in the graph H. Okay? And let us see what this set of edges is. So what are the edges here? Why would it be W2 U1? The ones that go to W0, the two edges that are going to W0, right? So our deficient set that we have chosen, let me just mark in red. Right, so this is our deficient set. And these are the neighbors in the graph H. So we're looking at all edges going from S, not to the neighbors of S in H. So that which means they have to go to W0. Right? So we've got U0, W0 and U2, W0. Okay, let's look at their slacks. Anyone can tell me the slacks? The first one is 6. And the second one is 1. Right? Okay. Yeah. So we'll choose the minimum slack. And that is going to be our beta. And we'll add beta here. And we will subtract beta from all of these guys. And so let me write down the new solution by cancelling the previous one. Let me just, so what are we changing? We are changing all of these values, right? We are changing all of these and we are changing these two. Okay, we have added 1 here. So this becomes a 0 plus 2 plus 2. And we are subtracting 1 on this side. So we have a minus 4 and we have a minus 2. All right, so we have a new dual feasible solution. What is the value of this one? We have increased, we have added 3 and we have subtracted 2. So in total, we have added 1, right? So whatever the previous one was, we have increased by 1. So it's going to be minus 3. Right? That is the sum of all the labels. You can check that 4, minus 4, minus 2, minus 1, minus 3. Okay, no mistake so far, I guess. All right, so let's draw the tight graph again. U0, U1, U2, W0, W1, W2. Okay, so for edges which had one end in S and the other end in neighborhood of S in H, they will remain tight. So these 3 edges will remain tight. Oh, U0, W2 as well, right? In fact, all the edges were like that. All our previous tight edges were like that. So they all remain tight. And one more edge should have become tight, U2, W0 in particular. Of course, you could have multiple edges having the same minimum value, and then they would all become tight. But in this case, we have exactly one, which is U2, W0. Does this graph have a perfect matching? Right? Everyone sees a unique perfect matching in this graph, I suppose. So it doesn't have to be unique, but it happens to be unique in this example. So let's write down. So it's U2W0, U0W2, and U1W1. These 3 edges is our minimum cost perfect matching, right? Because our perfect matching and the dual feasible solution at this stage, they satisfy the complementary slackness conditions. In particular, they both correspond to optimal solutions in the primal and the dual. Therefore, it has to be a minimum cost perfect matching, right? Okay. So this graph H has a perfect matching, which is U0 W2, U2 W0, and U1 W1. And since M, so let's call this M, and Y bar satisfy the CS conditions, M is indeed a min cost perfect matching, and Y bar an optimal dual feasible solution, right? Okay, so this is basically the algorithm. We will formalize it tomorrow. We are already at 10:48, so let's not bother with formalizing today. So tomorrow we continue. And we might also discuss running time related things here, because unlike the shortest path case, this is actually, I think the algorithm is actually a bit simpler. You don't need directed graphs and all that, but um, the runtime analysis actually turns out to be more complicated, because as stated, as we did today, is actually not a strongly polynomial time algorithm, because what the only thing you know at this point is that the dual feasible solution increases. But if things are not integers, the increment, you don't have much control over how much the increment is, right? So ideally what you want some discrete value to increase, then you can get some control over the runtime of the algorithm. But if you have some continuous value increasing, it doesn't give you a lot of control over the runtime of the algorithm, right? So it is a good algorithm, but it's not really a polytime algorithm as stated, right? There are ways to deal with it, and I'll try to cover that tomorrow. Honestly, I'm not a runtime specialist, but we'll try to do it. Okay. So, all right. Are there any questions or concerns at this point? I want to state one quick theorem and also make a couple of comments. So this is so once we prove the correctness of the algorithm, so the correctness is not an issue. So what you can show easily is that the algorithm will terminate, because you're always increasing the dual feasible solutions value. So it will terminate, and you can also show the correctness. That is also straightforward. So from that you can conclude that for any bipartite matchable graph, the LP relaxation um, the LP relaxation minimize C transpose X subject to AX, sorry, very used to writing, subject to AX equals 1 and X at least 0, where C are your costs, right? So C is a cost function from the edges to the real numbers. This always has an integral optimal solution. In fact, not only integral, it is a 0, 1 optimal solution, right? It corresponds to a perfect matching. So for any bipartite matchable graph, no matter what edges cost you give to the edges, so long as they are real numbers, this algorithm will terminate, and it will terminate with a perfect matching, which will be an optimal solution for the primal LP relaxation of the ILP, right? In fact, what you proved on assignment 2, you proved that the fractional matching polytope is equal to the perfect matching polytope, which actually means that for this LP relaxation, all the extreme points are integral, right? So, and we know that whenever there is an optimal solution, there will be an optimal solution at one of the extreme points. So you already proved something stronger on your assignment 2. Right? So follows from assignment 2 as well, because the fractional matching polytope as defined there is the same as the perfect matching polytope. Right? So for bipartite graphs, of course. Yeah. And this is not true for non-bipartite graphs. I think the assignment might have also asked you for an example. If not, we'll be seeing it in the lectures anyways. Assignment 2, I'm not sure if there was an example that you were supposed to construct. Right, you were supposed to write. Okay, good. I've forgotten what all I put in the assignment exactly. All right, so that's all for today. Are there any questions or concerns? Anyone in the call? I'll stop recording.